Good. So welcome. Welcome everyone to this first edition of Digital Science for Drug Discovery. So our aim is here really to bring people together that are interested in the topic of digital science for drug discovery across disciplines and also personally. So originally our aim was to have in-person meetings in Berlin. And this is still our goal as soon as the situation allows. And let's see when that will be. So who's we? That's Andreas, Andrea, and myself. And if we are not organizing seminars, we are associated with these organizations. And before we start with our speakers, I would just want to introduce you to some housekeeping announcement and some further information. So we have our first edition today, but we're already planning ahead for the next edition. So if you want to save the date, our next event is planned for the 25th of November, and all the dates and registration details can be found on our webpage. And as Andreas mentioned, we are trying to make the recordings available. And for your questions, please type them in the chat and we will go through them then after the talks. And ideally, also, if we don't have enough time for all the questions, it'd be great if the speakers could follow up on the remaining questions. And yeah, very important, if you like this meeting and if you think you have a good topic that you would like to present, please let us know. Or if you just want to have information, get in touch with us. And again, all the details on how to contact us can be found on our webpage. And with that, I would like to hand over to Andreas to introduce you to the program and to our first speaker.
Yeah, absolutely. Thanks for the introduction, Clara. So we have two excellent speakers, I think, in this first edition. And the first speaker will be Mohammed AlQuraishi from Columbia University. And I came across Mohammed's blog posts actually about half a year ago or so, where he discussed AlphaFold and the practical impact that may or may not have, or may have only in particular areas in the drug discovery context. And that was actually the main reason to invite Mohammed to give a first presentation here. And afterwards, we will continue with Pat Walters from Relay, who will talk about challenges and opportunities for machine learning and drug discovery. But firstly, I would like to hand over to Mohammed. Mohammed, and oh, there's one thing I forgot to say. We will have two talks, but afterwards, and that is very important, we will have a virtual pub session, so to speak. So we will put people into breakout rooms randomly, so 6-7 people or so, so you can meet friends from long ago who you didn't see for years, as well as meet new people. So we do that with the Cambridge Cheminformatics meetings as well. So of course, not everyone's staying afterwards, but it's very interesting also to discuss in smaller groups. So after the two talks, please stay online as well, because there will be this digital science mixer, as we call it, afterwards as well. Yeah, but now I would like to hand over to Mohammed, who will discuss about AlphaFold 2 and the impact it may have in the drug discovery context. Thanks for joining us, Mohammed.
Thank you very much for the introduction. So I will certainly talk a little bit about AlphaFold 2, and I will try to sort of kind of summarize maybe a high level what I think sort of AlphaFold 2 can and cannot do today, and then also go into a bit of the discovery aspect of things. But I think that's really sort of an ongoing discussion. Then I'll step back for a moment and just give a bit of a sort of a context in terms of where AlphaFold 2 fits into this kind of broader space of protein structure prediction algorithms. Hopefully giving a bit of a history, but also maybe kind of anticipating where things are going to move in the years to come. And then I'll spend the remaining half of the talk talking a bit about our own work in this space on sort of single sequence prediction instead of using multiple sequence alignments, which I think will actually have some implications as well for drug discovery and sort of other areas of biological discovery that have to do with things like protein design or orphan proteins. So let's get into it. So as I'm sure everybody here is aware, there has been this deep learning evolution that's impacted many fields of science, including protein structure prediction. In this field in particular, there's a sort of well-known contest called CASP that happens every 2 years, where people predict structures of proteins that they don't know. If you look at the history of, I don't have a full history of it here shown, but if you look at the history from like mid-2000s till 2016 or so, in the free modeling category, this is where you're trying to predict structures without any kind of templates, without any homologous structures. Really, things were sort of flailing around for a very long time. We were seeing prediction accuracies, that are essentially sort of corresponding to just noise, more or less, in 12, 15 angstrom range. Then in 2018, AlphaFold, the first version of AlphaFold from DeepMind came on the scene. And this, I think, was kind of the first method to really leverage both kind of convolution ideas and as well as machine learning to really push this sort of way beyond what we thought was sort of possible using these approaches. You know, there's certainly methods prior to AlphaFold, but it was sort of the first one to kind of really demonstrate leaps that were sort of qualitative relative to kind of the non-machine learning based approaches. And I'll talk about this in a moment. And I think for many of us, myself included, we probably thought that much of the low-hanging fruit got picked by that point, and that it was going to take some significant innovation to go from this, about the 6 sort of angstrom roughly RMSD line to something, that is much better. And I think what was surprising was that DeepMind was very much able to do this, in fact, to actually innovate in a number of fundamental ways. And really get us to just the things that are beginning to sort of be within striking distance of experimental methods. Certainly not quite there yet, but at least accurate enough to be useful for certain biological applications. Sort of interesting enough to be useful. So what can AlphaFold do and not do as of today, at least? So I should say, in terms of actual kind of rigorous assessment, it's been primarily assessed in the single domain APRO context, right? There's been many kind of, I would call them unofficial applications of AlphaFold in other areas, including like protein docking and so on. But these are all not really sort of, these are sort of, for the most part, stuff that have been anecdotal. People sort of trying them in various ways, and very promising, obviously. But the rigorous assessment at Cas14 was very much limited to sort of single domain APRO proteins. Could be quite large, and obviously when you're looking at proteins that are that size, these are multi-domain proteins. But the assessment was done at single domains, and for that assessment, at least the median accuracy was about 2.1 angstroms, which was again, like, very impressive. This is sort of the full distribution that we saw at the time. About 90% are within 4 angstroms or so, so still reasonable, let's say. And with a handful of predictions, as you can see in the histogram, that was sort of beyond that 4 angstrom line. I think 5 or 6 out of the 100 or so in Cas14, and those really were, I would say, they could also be explained by various reasons, like having either NMR structures or they might be obligate heteromers, that require other proteins there to form or to fold, things of that sort. Obviously, since then, now AlphaFold has been applied to the whole human proteome, and I think the performance numbers we saw at Cas14 really held up, and I would even say the results from the proteome-wide application have exceeded these results, because in some ways Cas very much focuses on kind of the hardest targets, the ones that we haven't seen before. Well, of course, most proteins are in some ways similar to proteins we have homologs for. So I think that there was some discussion at the time at Cas14 whether this was sort of a representative assessment of the accuracy of AlphaFold 2, and I think this question has been answered definitively in the affirmative, and even more so, I would say, at least again for these sort of single domain APRO proteins. And you can see some of the examples here. There are some interesting sort of aspects of AlphaFold that I think are kind of sort of telling in terms of how it works, but also maybe suggestive of ways to move forward. So one question is, again, predicting either heteromers or multimers. And this is one example. This is a trimer. And what you see here, which is sort of interesting, is that the structure is actually quite good. But of course, from the perspective of AlphaFold, it's sort of being tasked with predicting the monomeric structure, yet it's sort of predicting the monomeric information that is actually corresponding to the trimeric structure. And this is something that is both sort of a blessing and a well, for if you have heteromers, potentially you could actually disambiguate these things, you can disentangle these things, and that's what people have been applying this in these various contexts. But for homo multimers, it's actually just a little bit difficult, because the kind of evolutionary signal is there within a single monomer to kind of link it up with the other monomers. So it's really hard to disentangle what the structure would look like on its own, what an individual domain would look like on its own, as opposed to the kind of trimeric configuration. And this is something that, with AlphaFold, it's not trying to predict something physical per se, right? You give it a monomer, if it thinks this thing is going to sort of link up in all sorts of other ways with other molecules of the same type, then it will simply give you the confirmation of the trimeric version. And you can see sort of in other areas. So this is another example where here it sort of has an active site. It binds a zinc ion. from the perspective of AlphaFold, the zinc ion is not present. It doesn't know anything about zinc ions. It only deals with natural amino acids, but it sort of knows that that active site, from its knowledge of the PDB, ought to look a certain way, and it sort of almost imputes the zinc ion, even though that never does so explicitly. And this obviously has implications for ligand binding, for drug discovery applications. But being able to do so systematically is going to be challenging. The idea is about using, for example, a sort of a free-floating amino acid as essentially kind of a probe that acts a bit like a ligand, an arbitrary small molecule. But of course, that's going to be a very kind of generic probe. It's not going to reflect the actual chemistry of any given small molecule. It does, I think, to some extent struggle with multi-domain proteins, although I think this is interesting in the sense that it's becoming increasingly, I think, clear that we sort of underestimated the role that disordered regions play in human proteins, mammalian proteins. People have seen these sort of pictures coming out of the AlphaFold 2 EBI database where you see so many unstructured loops, and I think it gets to the point that many of these proteins really have fairly flexible regions, and they are more like a sort of a collection of individual domains as opposed to a single kind of rigid object. And so insofar, I think as there's not, say, sort of agreement between experimental structures that are multi-domain proteins and predictions, I think it's sort of behooves us to kind of consider whether it may be that the experiments the experimental structures are maybe oversimplifying the underlying kind of physiological picture. Now, where it's not been tested really in any meaningful way, AlphaFold 2 hasn't been tested are with mutations or things like design proteins. And can't currently really sort of handle, at least officially, again, complexes, and certainly not ligands or cofactors and things of that sort. And in particular, kind of just at this talk, really about single sequences. So not going from multiple sequence alignments, but from proteins, from individual proteins. In particular, if one is interested in aspects that are specific to those individual sequences that are not reflected in the multiple sequence alignment, in the family level structure. So now let me kind of back up for a moment and then kind of contextualize where AlphaFold fits in the sort of algorithm space of protein structure prediction, because I think it helps a little bit to sort of look at where we've been and I think kind of maybe anticipate where we may be going. So there are many ways, of course, to do this, and I'm going to do it in sort of along two main axes. One is sequence information at inference time, so how much kind of data goes into making a prediction, not doing training, but doing inference. And that's on the x-axis. And on the y-axis, I'm going to sort of consider accuracy. How well does it work given that much information, right? So historically, much of the focus in the space was on kind of physics-based approaches, right? For decades, methods like Rosetta were kind of the gold standard for trying to get at this sort of question. And they really did try to go from a single sequence to a prediction. The idea of coevolution didn't become serious till I would say about 10 years ago or so. But the accuracy of these methods was limited, and it remains limited. It's still very hard to take Rosetta right now, the vanilla version, and try to actually fold a protein, right, from scratch. Templates help. So if you have a structural template that you can sort of crib off of, that does help. But without these templates, it's really very difficult. This, of course, began to change, about 10 years ago or so with the kind of the practical debut of coevolution-based approaches, the idea of multiple sequence alignments, and then looking at the covariation between residues in that alignment and kind of relating that to protein structure, to proximity in 3D space. The initial sort of slew of approaches like Gremlin or EVFold were not supervised. They're not really using any machine learning. They were simply just trying to take, doing these statistics on the multiple sequence alignment, and from that extract essentially kind of propensities of residues to be in contact, which I then typically fed into physics-based approaches at the time anyway to predict the structure. This I think sort of truly began to change with the AlphaX16 from Jim Bazou's group in 2016. And this was sort of the first method that now took this idea but then combined it with deep learning, right? So sort of kind of reframed it as a supervised machine learning problem where we take structures from the PDB and then we learn directly a sort of a relationship from the covariation kind of matrix to the structure. So not simply trying to kind of do a statistical say sort of exercise, but actually trying to kind of learn patterns that have to do with sort of higher order maybe correlations in the covariation map. And the AlphaX16, I think demonstrated actually quite a bit of improvement, but didn't sort of that improvement didn't really sort of show up in CASP. It took a few years. AlphaX18 kind of took that idea and advanced it to go from sort of binary contacts between residues to continuous distances. So making sort of more of a refined idea, which was actually the basis for the first AlphaFold. So in terms of kind of technical innovation, that was the main key idea of AlphaFold 1. and both after X18 and AlphaFold 1 were sort of developed contemporaneously, but AlphaFold was better engineered in a way, and that allowed it to work better. This then sort of like things like Rosetta, which sort of further elaborated on that idea. In parallel, sort of around that time, just before, in fact, AlphaFold and after X18, I had developed this sort of technique which had sort of two notable points that I'll come back to in a moment. One was that it sort of was trying to go in the kind of the leftward direction towards single sequences, away from coevolution. Didn't quite make it work all the way to single sequence at the time. So instead, it relied on position-specific scoring matrices. So essentially, if you think of covariation and coevolution as sort of second order evolutionary information, looking at how two residues correlate with one another, PSMs are really first order, just looking at the individual residues and asking how do they mutate, what are their propensities for mutations. So that's one thing that RGN did, is go in that direction. But more notably, I think it was the first method that really was end-to-end differentiable. So sort of kind of reformulated the entire pipeline in terms of deep learning primitives. As I alluded to earlier, these methods, while they did have aspects of them be framed in terms of kind of supervised learning, the final structure prediction was still being done by physics-based approaches, including for the first AlphaFold, in fact. So they did not go all the way from the MSA to the structure. They essentially went from the MSA to something like a contact map, and then use that contact map as a constraint to follow a protein using a physics-based engine. RGN and a related method from Debbie Mark's group called NEMO by John Ingram were the first end-to-end differentiable method. So they sort of reformulated the entire approach using neural networks. And in fact, this method, NEMO, actually tried to go all the way to a single sequence level, but certainly suffered a performance penalty as a result. So fast forward to late last year, we have Raptor X20, which is sort of another elaboration of this general idea. And in fact, Raptor X20 was applied to PS systems as well. But obviously, kind of the big story, and that's sort of what's really kind of revolutionized the field, I would say now, was AlphaFold 2, right? And AlphaFold 2 did a few things, but actually more than a few things. The innovations were quite extensive along, I would say, 5 or 6 different dimensions. But one of them was to say, all right, we're not going to look at coevolution simply, but we're going to take the full MSA, the full multiple sequence alignment, and really extract as much information as possible out of that multiple sequence alignment. So not simply just looking at second order effects, but potentially higher order effects. And additionally, AlphaFold 2 was the first end-to-end differential approach that goes from MSAs, as opposed to PSSMs or what have you, to the final structure. So it wasn't the sort of general framework of really kind of reformulating the entire system using neural primitives. And I think in some ways, looking back at this, I think, and moving forward too, I suspect this idea of kind of neuralization of those various components is going to be increasingly important in this field, and in particular in applications related to drug discovery. For example, if one is thinking about docking, which I'll come back to later on, being able to sort of neuralize the docking process, and certainly people have been working on this now, I think will be very critical, even potentially neuralizing things like MD simulations. But sort of coming back to sort of now, for such a prediction, I think for me at least the holy grail really is being able to be as good as AlphaFold 2 or even better, but go from a single sequence. Right? That's sort of the original problem. And here is sort of where we've been trying to push. This is what I'm going to tell you about today. RGN2, which was pre-printed a few weeks ago. We're certainly not anywhere near AlphaFold 2 across the board, but at least in certain areas where one really does need to rely on single sequences, we seem to be doing actually better, and I'll show you that in a moment. So let me just sort of decompose the algorithm space into sort of its constituent components. So you have the inputs, that's what goes into the system, as I was talking about earlier. You have some sort of torso, the thing that does the computation, that does the reasoning. You have an output, this is the thing that comes out of that reasoning engine, and this is the part, right? The green, yellow, blue sort of section that is a neural network, or that is, let's say, at least differentiable. This is a system that gets optimized within a supervised machine learning framework. The post-processing, the stuff in pink, is something that happens afterwards, and maybe a fairly light touch, or maybe a very heavy touch, like actually predicting the structure itself. But the point I would emphasize is that the output is what gets optimized within the machine learning framework. This is the thing over which the kind of the optimization, the gradients are being sort of propagated. Right. So this is the end-to-end differentiable piece. Now, if we look at these methods, the ones I'm highlighting here in the top right, the way they sort of essentially work, right, is that take a multiple sequence alignment, extract a covariation matrix, and then predict something that is a proxy to the structure, but that is not the structure. Something like I said earlier, a binary contact map, or maybe a distance map, into your Rosetta, they include distances and orientations and orientagram. So which are objects, but still proximal to the 3D structure, not exactly the 3D structure. And this meant that they have to go through some extensive post-processing to finally get the structure out, which can be quite slow just parenthetically in terms of compute time. But more critically, this prevents optimization of the final structure within this machine learning framework, right? Because this is something that doesn't have back propagation, doesn't go through it, right? So this is something that does not get tuned along with all the other components in this process. Additionally, on the output level, right, because we're not predicting the structure, in particular in this case, because these methods were simply predicting distances, there's no guarantee that they're self-consistent. These distances could actually disagree with one another. And that's something that that I think led to some performance sort of being left on the table, because just simply enforcing self-consistency would result in better performance naturally. So those, the method RGN, NEMO, the ones that came out a couple of years ago, what they really start trying to attack is this question of, can we actually go directly to structure and therefore be self-consistent and force the self-consistency along the entire scheme. Now, instead of our approach at the time, the way we did this was to essentially formulate the problem as a sort of a sequential prediction task, where we had for each residue sort of a choice of torsional alphabets, letters that describe what the torsion angles are, the local geometry looks like around any given residue, and there's sort of a finite but discrete set of those torsion kind of triplets, and then what essentially happens with the prediction task was at any given stage was to simply kind of predict a distribution over those letters, those structural letters, and then essentially project them onto a sort of actually a complex plane. There's some technical details here, but you can imagine this being kind of being projected onto the circle, and then simply averaging those letters, those torsion angles based on the weights that the model predicts, and then extracting an angle based on that construction. For the sake of time, I won't go into too much detail, but just suffice it to say that there's some approach in which we're essentially able to extract angles at each residue by this sort of kind of reasoning process that is essentially discrete at every step, which is quite important for the optimization procedure to sort of proceed smoothly. But by the end result of this was that every residue predicts essentially 3 torsion angles, which then allow us to sort of build up the backbone, step by step, one atom at a time, by performing torsion rotations, bond rotations, and bond extensions, and then just kind of repeating this process iteratively until you basically get the whole structure out as I just skipped ahead. And crucially, all the equations that describe this process were differentiable, so we can kind of back propagate this through this process and get the structure out. This, I should say, contrasts quite a bit with how AlphaFold does this, AlphaFold 2. So AlphaFold 1 didn't do any of this stuff because it was not differentiable, but with AlphaFold 2, it is differentiable. And the way they do it, they don't do it sequentially, they simply kind of spit out all the structures, all the residues, and then sort of in parallel refine them to sort of, to fit into the last the last positions, or the most accurate positions, or the most favorable positions, let's say. And I think what was surprising in a way with AlphaFold 2 construction is that it works, is that you could actually just spit out a bunch of coordinates and then have them not sort of all clump on top of one another, sort of learns essentially sterics just from the PDB. This approach sort of bakes in the fact that you have to have kind of certain distances between the residues and so on, but has the drawback of being sequential, which potentially limits the ability to sort of capture long-range distances, which I'll talk about momentarily as well. But anyway, so this first approach relied on these position-specific Cohen matrices, which were okay, but it was sort of a handicap, but it's some sort of compromise between single sequence prediction and then co-evolutionary kind of contact maps. And there are different choices in terms of how one does this. At the time, we're using an LSTM, but now much of the field, including ourselves, we've moved toward attention-based approaches called transformers. Let me actually skip it because I don't think this is super relevant for now. So that was kind of the first one. Now let me tell you the new work that we're developing, and we're about to actually release an updated preprint with some additional details. So one key component here is that we sort of reformatted the construction in terms of the backbone buildup to be actually much more efficient. In part by simply just focusing on C alpha atoms, but also sort of associating with each C alpha atom a reference frame that then controls essentially the kind of the build-up process, because I won't go into the math for the sake of time, but essentially, let me just essentially we can sort of reduce the process of backbone construction to a series of matrix multiplications which is a much simpler computational kind of construction than the previous one I showed you. But it also actually allows us to generate structures that are much better behaved locally, that we don't have the kind of secondary structure pathologies that we did in the first method. This has some parallels with the AlphaFold2 approach in terms of these reference frames, and all the other constructions were sort of being developed independently. More critically, and this is kind of the key piece for this new system, is that we now actually do go from single sequences without any explicit evolutionary information, at least. And instead, the single sequence is mapped through a language model, which we call AminoBird. Now, if you're not familiar with language models, this is an output of one of them called GPT-3. So GPT-3 is trained on English, lots and lots of English text. And what's amazing about it is that if you sort of prompt GPT-3 with a small amount of text, that's the one shown in dark gray rather, it sort of just generates, or is able to generate, remarkably flowing text, grammatically correct, semantically reasonably coherent, and it could go on for pages and pages. And what's remarkable is this approach is done in a very simple way, which I'll describe in a moment. So this was done in the natural language context, with natural languages, but us and other groups have applied them in the past and now are applying them in this context for proteins. So the basic idea is you take a sequence, you essentially mask some fraction of that sequence. So you hide the residues at those positions, and then you feed this to some sort of architecture. In our case, it's a series of transformers. Again, these attention-based neural networks. And then ask the model to sort of recover that masked sequence. So recover the residues that were hidden. And what this does is essentially it learns to associate a sort of a rich latent representation with every residue in the sequence. And in particular, this representation not only captures, that this is a valine, for example, but instead that this valine has a context, that has the SQ to downstream of it, and this sequence upstream of it. And it's that context that allows us to build sort of very rich representations for each residue. Now, we don't just do this. We do other things. For example, we mask contiguous fragments. We also sort of splice in two different sequences and ask the model, is this a real protein or a spliced protein? Things of that sort. But the basic notion here is that by doing this procedure, we're able to train a model to sort of learn to transform individual sequences into much richer representations. And of course, it's fair to say that part of what this kind of method learns is evolutionary relationships, but implicitly so. But it also is likely to learn other things, other aspects of protein structure or protein sequence rather, that can then be useful for the purposes of structure prediction. Now, I should say, for the sake of performance, for the sake of accuracy, we do also provide a sort of an optional post-processing step to do physics-based refinement. This is not strictly speaking necessary, but we do find that it helps. And it actually helps quite a bit in some cases. AlphaFold2 incidentally does something similar as well, although I think ours is a bit more extensive. We benefit more from refinement than they do. For this case, the refinement is really quite lightweight. All right, so let me sort of just show you. I'll end by showing some results. For Cas14 in particular, I'll show you first some cherry-picked examples. So these were cases where we did quite well. The RMSEs are relative to the ground truth, and we're in pick and AlphaFold2's in green. But the point here isn't that we're doing sort of competitively. We're still not doing actually as well as AlphaFold2 in these cases. But the point is that we're predicting from single sequences, not from MSAs. That's really the key thing, right? And I should say, in these instances, there are rich MSAs, and so AlphaFold2 is able to really benefit from that information to provide better structures.
Oh, hello, Mohammed, are you still there?
I think we lost him.
Yeah, let's see. Let's hope he comes in again in a second. Yeah. Let's just wait a little bit.
My apologies. I think I dropped. Can you all hear me?
Welcome back. Yep, works fine.
Great.
Yes, sorry about that. I think my internet spaced out for a moment. Okay.
Yeah, but now it sounds good again. Yeah, just share again. Continue from where I left off. Great, thanks.
Yeah, I'll do that. Okay. So hopefully, well, I believe the last thing I was saying was that for the examples I was showing, the MSA, one can argue why handicap oneself, why not use these MSAs, and of course I think that's perfectly a reasonable thing to say. But there are certain cases where one simply doesn't have access to an MSA, and I'll show you two instances of it.
Mohammed, you're not sharing the slides right now, the screen.
Oh, I'm sorry.
Yeah, just.
So I don't know what's going on. You can hear me, right?
That's right. It's the green button at the bottom, the share screen button.
Can you see
now it's coming? Yeah, orphans and de novo proteins.
And I was muted. Can you hear me?
Yeah, we can hear you.
Sounds good.
Let's hope this goes smoothly. Okay, so let me show you some results on orphan proteins. So these are proteins on which there are for which there are no homologous sequences. And what you see here is that on these, actually, we do in fact do better than AlphaFold2, fairly significantly better. So let me just unpack this. So here we're looking at the delta in GDTS and the delta in DRMSD. So these are two different metrics. And so in the top left are instances in which we do better on both metrics. On the bottom right are instances in which we do worse on both metrics. And these are sort of split results. And so for about 60%, we do best on both metrics. Of course, these are fairly unique instances because these are proteins that have no homologs, at least known homologs, but still, at least it demonstrates the power of being able to go from single sequences. De novo proteins are sort of interesting. So here we split them by helix-rich and beta-rich proteins. And for helical proteins, we actually do quite a bit better on de novo proteins. On beta-rich, AlphaFold2 does better. And this I suspect might have to do with something I was referring to earlier, which is that because we're constructing things sequentially, we may be having a harder time capturing long-range interactions, and this I think pans out here. So obviously, a natural direction that we're sort of looking into now is sort of combining some of the architectural innovations from AlphaFold2 with sort of these kind of language models to be able to go from single sequences. Now, one thing to know though about what I'm showing you here, all these de novo proteins were not in the AlphaFold2 training set. So these were things that AlphaFold2 did not get to see. When we do compare performance on a training set, on a validation set in which AlphaFold2 had access to the training set, to the validation set rather, the performance is much more lopsided. And AlphaFold2 does much better. So of course, this is not a fair comparison because AlphaFold2 has seen these structures, but I'm mentioning it here because it does seem to indicate that there is some overfitting from AlphaFold2. Because the performance is quite different than this situation, right? And so because I know a lot of people have sort of predictive structures, but structures that exist in the PDB, and the comparisons between these based on these kinds of these predictions. But obviously these are based on things that are in the training set, and I think one ought to take some care in that because there is some evidence that there is overfitting on the part of AlphaFold2. Okay, so let me sort of I know a little bit over time with the delay. So I'll just sort of briefly kind of mention the implications of this and stop there. So like I said, we don't do refinement, or we don't have to do refinement. And without that, the speed up is quite substantial, so even relative to AlphaFold2 today, days to milliseconds, or at least multiple hours to milliseconds. And I think for the drug discovery context, one thing I think is quite important is the idea of flexible docking, right? So if you want to be able to dock to a molecule, you want to be able to predict structures that are really conditioned on that molecule and where that molecule is in space, and also to location of the protein. And being able to do this very quickly, I think, is quite key. So that's one area where I think kind of speed matters, because in silico screening, you want to be able to not only screen billions of things, but also do them in billions of different conformations. And that's something that I think won't be possible with sort of the heavy duty methods like AlphaFold2. Another area which we're interested in is the effects of genetic variation. So how do sequences vary due to mutations, and particularly minor mutations that change the localized regions of the structure, for example. And that's something that I think so single sequence-based approaches have a lot to offer there, as well as things like, obviously, like rapidly evolving proteins, including in viruses. We're in the midst of a pandemic, and protein design, as I was suggesting with the de novo analysis. So I'll stop here. I should say, all the work was done by postdocs and students in my group, primarily Gatul, Nazim, Serge, and Charlotte. And this work was done in collaboration with George Church and Peter Sorga Labs at Harvard. So I don't know if there's any time for questions, but I'll stop here.
Okay, very good. Excellent. Thanks for your presentation, Mohammed. And I think the first question that was listed is actually the one by Daniel Grofert. And I wonder if you have a microphone, so it makes it a bit more personal. Feel free to spell out your question, because there might be additional information you would like to bring across. It's about the de novo design of proteins. Daniel, do you want to verbalize your question? Otherwise, I can read it in case that's inconvenient, of course. Can this be used to predict de novo protein designs? That was Daniel's question.
Yeah, thank you. I wanted to ask that question. I'm just curious to know whether this works for this type of designs, de novo designs.
Yeah, I think so. I mean, that was the, obviously this was the slide I showed earlier, right? So I think at the current moment, I think it works better for helical rich than beta rich proteins. But it seems to work quite well, actually. I'm better than AlphaFold 2 as far as we can tell, at least the ones that are not in this training set. So.
Okay, thanks a lot. And the next question is from Massimo regarding different metrics, and that's always a tricky question, of course, if you benchmark the output of machine learning models, right? Massimo, would you like to elaborate on a question orally?
Oh yes. So basically, attending other lectures from AlphaFold, I learned that they always try to not use RMSD to compare the quality of the models, because they say that they are able to predict correctly the domain, the quality of the domain, but not the relation among different domains. For example, if two domains are connected by a flexible linker, or for example, if there is some situation in which you have, they're able to predict, for example, just one possible conformation, but not all the possible states for the protein. So they always say to use this PLDT metric together with the PAE metric, so matrix. I don't know if you have any comment about this.
Yeah, no, I think that's a fair. That's an important point. So I should say, everything here is single domain, so it's not particularly relevant in terms of the the issue of domain movements. I think generally speaking, that is an issue for any metric that tries to summarize accuracy over the whole structure, right? Because you're going to end up with a situation in which those things can move. I mean, of course, something like IDTT, which is as specific, you do also potentially lose a bit on the global side of things. So if you actually do care about the relative orientations, then you would miss that with something like this. So I mean, there's pros and cons to each. And that's partly why we're using sort of two metrics here. But I should say, for at least the examples I'm showing, it doesn't really matter, because these are all single domain examples. We're not actually predicting anything that's multi-domain for those proteins. Usually the de novo proteins tend to be quite small anyway.
Okay, great. Thanks a lot. And from Thomas, I think there's a somewhat related question. What is taken into account for calculating the performance of the method? Thomas, do you want to elaborate on your question?
Yeah, I mean, it's pretty straightforward. Thanks, Mohammed. It's about so that the backbone is half of the story, and the other half of the story is sidechain. So can you, which is obviously important for any sort of application. So can you elaborate on any results on AlphaFold or other tools results there, or is there some other straightforward process that you would take on after having predicted, the backbone to place the sidechains?
Yeah, so there's nothing showing actually over the side chains. So I didn't quite capture the first part of the question, but with AlphaFold, so AlphaFold 2, does this process where they initially generate the backbones, and then they kind of project where the sidechain atoms are, but in a neuralized fashion. And they do remarkably well. I mean, their sidechains are very good, are much better than than I think anything anybody's seen before. In our case, the neuralized part is only computing the backbones, and then we use the post-processing refinement to compute the side chains. So that's sort of more physics-based. It's not neuralized. But the results I'm showing you are over side chains. So I mean, it seems to work well enough. But certainly, I mean, I think one thing we want to do is do them in a normalized fashion as well. It makes perfect sense, and it's, one seems to be able, like the sessions that are coming out of a fault 2 seem to actually be better than anything you can get with a physical potential. So why not do that?
Yeah, thanks a lot, Mohammed. One comment, by the way, I found very interesting on your blog was that for fault predictions, because we discussed the impact on drug discovery, right? Is that for fault prediction is actually the gold standard. So what you want to achieve, right? What you want to model is quite clearly defined, right? You have a structure and you can calculate, for example, the RMSD, yeah? Whatever the caveats are with that, right? But in many other tasks in drug discovery, that state, what you want from a compound, for example, is actually less clearly defined, right? That was one very interesting point I found on your blog. No, that is right. Do you want to elaborate on that as well?
Sorry, I heard everything but the last 2 sentences.
Yeah, right. No, that in some cases you don't actually know what you want, basically. Yeah, if you have AlphaFold, right, or structures, right, you want to have a structure that's the target state. That's what you want to predict, right? That's the output. But in some cases, when you were discussing the impact on drug discovery projects, it's actually less clearly defined what you actually want, right? Where you want to go with the model, right? What's the the gold standard, right? And that's less clearly defined when you were discussing the practical application in drug discovery context. So.
I agree completely, and I think this is going to be one thing that moving forward we're going to essentially have to sort of figure out, right? I mean, in some ways, I think there are existing sort of questions that people have asked, and particularly in the drug discovery context. Where does a small molecule dock? Where if not a fault 2, then sort of future versions of it, perhaps, for example, fine-tune specific protein families that can give you sort of very high accuracy there would be suitable for that kind of problem. But there are other questions that are much more about, what can we do with a whole bunch of structural data, right? How is that useful on the kind of systems level? Or even, I mean, I think one thing that's sort of interesting and sort of more in target discovery, right? Can we find new drug targets by just looking at sort of structural homology? I think there was actually a paper came out recently using AlphaFold 2 for that purpose. Can we look at full homology and sort of discover new ion channels that could potentially be sort of new drug targets that we didn't know about? So I think, I mean, in some ways, part of what we're going to be doing is substituting AlphaFold 2 structures in lieu of homology models or whatever in existing pipelines, and I think that's going to be interesting. But I think moving forward, what I think is very exciting is about can we come up with sort of new use cases that really leverage structure at scale, and that we sort of couldn't really think of before because we simply didn't have that information available to us. And I'm quite excited about this kind of notion of structural systems biology. Can we think of dynamical systems based on structure? Can we even begin to think about like simulations at the level of structural ensembles? And that we're not quite there yet, but I think we might get there much more quickly than we had previously anticipated.
Yeah, that's right. And if we think about selectivity, for example, there are certainly cases, right, where ensembles of structures or system structure biology, right, are quite likely to have some impact. Yeah, that's right.
Toxicity prediction, for example, things like that. Yeah.
Okay, let's do 2 or 3 more questions. Pat, you have a question as well, right?
Yes, I do. So you briefly alluded to being able to model structures of point mutations, and in oncology, genetic disease, these are incredibly important factors. So I was wondering if you could expand just a little bit and talk about where you see the potential of protein structure prediction with these mutations.
Right. So I mean, so the kind of the MSA coevolution-based paradigm, right, by construction essentially averages across a whole family of sequences, potentially hundreds, million, not millions, but hundreds of thousands, or at least thousands of sequences, and so that often ends up kind of averaging away all those little details, all the variation that's there. And the approach we've taken here with this method, IGN2, we're going from a single sequence, we're trying to make a prediction, right? And at least in principle, if one can learn a map from sequence to structure, then we should be, a general map, then we should be able to capture, the effects of mutations, as well as we can capture, major changes in fold shape. But it's fair to say that across the board, we're not quite yet as accurate as something like AlphaFold 2. And so one direction which I think is quite potentially plausible is to really try to kind of combine those approaches. So what the basic idea would be use something like an MSA-based approach to essentially define the overall fold of the protein, to get the core structure, and then you take that as essentially an input to something like RGN2, which then sort of knows roughly where it needs to be in structure space, but it has a sort of more refined notion of how individual sequence to structure variation really works, and then uses that kind of course prediction to then spit out something which is more kind of specific to that individual sequence. So that's one sort of possibility that one can push in this direction. But there are others. I mean, you could also imagine, going back to kind of more physics-based approaches, you could take something like an AlphaFold 2 prediction, and if you have reason to believe that that prediction is not really reflective of the actual sequence you have, then perhaps using physics-based approaches to even MD, sort of relax it onto that confirmation might be a good approach. And we're sort of thinking about different ways right now. One problem is that we don't actually have a good data set to assess this, to really be able to see how does minor sequence variation lead to structural variation, but that's something that we're sort of working on right now to really be able to kind of characterize this behavior, the behavior of algorithms on this task in a kind of systematic way.
So if somebody has a test set for Mohammed, can they reach out?
Yeah, please do. Absolutely.
Okay, cheers. Thanks a lot. Let's do one final question, and then and that's the one by Paul Kim. Would you like to verbalize that, Paul?
Yeah, thanks. Do you have any plans to augment your data set for the RGN using AlphaFold's like high confidence predictions on UniRef, for example? And do you think that AlphaFold's predicted structures are good enough to use in this way as like sort of data augmentation?
Yeah, I think so. Yeah, so the answer is both. I mean, yes to both. We do have plans, and I think it will be. I mean, they use it themselves for self-distillation, right? So and that seems to help. The trick is going to be to not, so again, overfit, because we don't want to end up just being essentially replicating what they're learning. So in my mind, at least, I think it might be this kind of two-stage process where if the model is kind of broken up into two pieces, one piece is sort of more about the kind of global prediction, and another piece is about the fine-grained prediction. And for the global prediction, I certainly think getting predictive, using predictive structures as input makes perfect sense. But then maybe there's kind of a second stage, which is really more about the fine-grained prediction, and that would only be trained on either XML data or perhaps data is augmented by more kind of physics-based approaches.
Okay, Paul, does it answer the question? Yeah.
Yes, thank you.
Excellent, fantastic. And I think there's still a couple of questions. Mohammed, it would be great, in case you still have a bit of time, to answer to those questions, maybe in the chat, which everyone can read as well. And so that is something we can discuss now. I think for the main program or the next speaker, great. Thanks a lot, Mohammed, for presenting it.
So it's my pleasure to introduce our next speaker, Pat Walters. Pat heads the computational informatics group at Relay, and before that, he was very long at Vertex, heading modeling and informatics. And I guess this is also where we first met, Pat, when Vertex was generously hosting the free energy calculations in drug discovery meetings. And Pat really does loads of contributions to the community. I mean, just to mention two things, he was a fantastic chair of the Gordon Conference of CAD in 2017, and many of you also will know his practical chemoinformatics blog. And if you want to know more about Pat and want to know why it's not always necessary to have a plan, but rather it's important to keep an open eye for opportunities, don't miss Pat's interview in Rockstars of R&D, which I enjoyed very much. And with that, I'll stop here and I'll hand over to Pat, and who will talk to us about challenges and opportunities for machine learning in drug discovery. Pat, please.
All right. Can you see my screen?
Not yet, at least not here in Berlin.
Okay. I am screen sharing, at least allegedly.
It's coming, I guess.
Is anybody seeing it yet?
Yes, it's coming. I can see it now.
Okay, great. Yeah, so I want to talk about some practical aspects of applying machine learning methods in drug discovery. I think these are things that don't get talked about enough. So this is probably more an opportunity for me to get things off my chest. So you are all part of my therapy session today. I want to thank Clara and Andrea and Andreas for inviting me to speak today. I'm excited to give this presentation. So I think, as we've all seen, machine learning is everywhere now. So Google Photos is using machine learning to help you to find pictures of your Uncle Frank. Alexa's using machine learning, sometimes not as effectively as it could, to understand speech. Machine learning has really revolutionized fields like radiology. Machine learning is helping us figure out which movies we want to watch and which songs we want to listen to and what we want to buy. And it's had a lot of impact also on drug discovery. I can remember 7 or 8 years ago when my group was working on phenotypic screens, and we would spend months hand tuning algorithms to identify specific features in cells. You know, these days, with available toolkits and with deep learning methods, you could probably do the same thing in an afternoon. For more than 50 years, people attempted to develop computer programs that could design routes for organic synthesis with limited success. And yet over the last 5 years, with the application of neural networks to huge corpuses of reaction information, we've gotten to the point where there are now multiple commercial products that can use neural networks to reliably define routes for organic synthesis. There's been some really exciting work by Adrian Roitberg and others on using machine learning to estimate quantum chemical potentials and to do these sorts of calculations in seconds rather than days. But what I want to talk about today is predictive models. This is something that we use all the time in the pharmaceutical industry. We're developing machine learning models to predict biological activity, to predict off-target activity, to predict selectivity, to predict pharmacokinetics. And I think we've come a long way, but I think that there are still a lot of fundamental open issues. So I want to talk about some of those fundamental open issues, as well as some things that I find really interesting research directions. So just to set the stage and make sure that we're all on the same page, what we're going to be talking about is using machine learning models to make predictions. So typically what we're going to start out with is a set of molecules that have been run through some biological assay, and we've got some experimental observable. So let's say that we're looking at something like the log of the aqueous solubility of a molecule. Then we calculate a set of features for those molecules, and we use a machine learning model to establish a relationship between that set of features and the chemical structure. Then, given a new set of molecules or ideas for molecules, we can then use our model to predict the activity of those molecules and prioritize those molecules for either synthesis or purchase. So today, though, I want to talk about 3 things that I think are really important that are still open issues in the field. The first is interpretable models. A lot of our models are black boxes. They give us a prediction, but we don't really understand the why behind the prediction. I want to talk a little bit about 3D and some of the open issues with using 3D structures to build machine learning models. And then finally, I want to talk about the idea of uncertainty in model applicability. So given a machine learning model, how can I, with confidence, say whether the machine learning model is going to be able to make a prediction on a particular molecule? So let's start out by talking about model interpretability. As I mentioned, a lot of our models are simply black boxes. So I have a molecule as input, I hand that to my machine learning model, and it gives me a prediction. So if I have the molecule on the left, imatinib, I put that into my machine learning model that predicts aqueous solubility, and it comes out with a prediction that the molecule is insoluble. That's not all that helpful. You know, what do I do? I go to a chemist and say, well, just give me every molecule you can think of, and then I'll give you a set of predictions. That is not helping our drug discovery effort. So when I look at this, there are a few reasons I think interpretable models are important. First, I've been working as a computational chemist in drug discovery for more than 25 years. in that time, I've discovered that I only have two jobs. My first job is to convince somebody to do an experiment. My second job is to convince somebody not to do an experiment. That's what I do. It's often difficult to tell someone, don't make this molecule because my neural network said it's going to be bad. You know, it's much more compelling case if I can use the physics and the chemistry behind this to convince somebody. But even more importantly, I want to figure out how to make the next molecule. So I want to know what's important and what's not important in this molecule. If I'm trying to do something like optimize the pharmacokinetics of a molecule, I may want to know the parts of the molecule that are important for binding so I can leave those alone. And then finally, in a lot of cases, our models don't work and we need to debug and we need to try to figure out why the model works or why it doesn't. And I think interpretability can really help with that. Now, there's been a lot of papers published recently on model interpretability, but I think a lot of the evidence for this is purely anecdotal. So what will happen is somebody builds a model for aqueous solubility, and then they use some simple method of identifying the most important descriptors, and the model comes back with a carboxylic acid is important for solubility. It's like, yeah, so I knew that already. So just, you know, suddenly because my model can predict something or say something's important that I already knew, my model's interpretable. So I think we need better approaches. I wanted to just talk a little bit about one approach that I think is really interesting. So there's a paper that just came out a few weeks ago on arXiv from Andrew White's group at the University of Rochester. And they apply what I think is a really interesting method. So they're using a method called counterfactuals. And a lot of the origins for counterfactuals actually come about through machine learning methods for predicting credit risk. One of the things that I learned a while ago when I started investigating this field is that, first of all, machine learning models are widely used in assessing credit risk. So MasterCard, Visa are all using machine learning models to decide who should get a credit card and who shouldn't. But the thing is, at least in the United States, legally, you can't tell somebody, I denied your credit because my neural network doesn't like you. You need to provide some sort of rationale behind this. So one of the techniques that's used for this is called counterfactuals. So in counterfactuals, what you're trying to do is identify a small change that will flip your prediction. So imagine I've got two people, one of them, we approved their credit, and the other person, their credit was declined. Well, you can look at all the features that went into that molecule. How much money do they make? How many credit cards do they have? Have they defaulted on a loan? You find two people with very similar characteristics that have different predictions, and you can then understand the rationale behind that prediction and explain to the people why their credit was declined. So the thing that I really liked in Andrew White's work was they did something very similar. So they started out with a molecule. So again, we'll start out with imatinib. This is predicted as insoluble. They then use a generative model. So there's this whole class of techniques that have been developed recently for generating molecule structures. And you can generate molecule structures that are analogs of a particular molecule. So what they do is they start out by generating a set of analogs. They then take that set of analogs and they do a prediction on those. So what I'm showing here is I've just generated this set of analogs. Now I'm going to predict their aqueous solubility. Once I've done that, I can then separate out the molecules that are predicted to be soluble and the molecules that are predicted to be insoluble. My molecule of interest on the left is predicted to be insoluble. So what I want to do now is try to find molecules that are similar to this that were predicted to be soluble. So then I can go and pick those molecules out. And now I can see that I've got imatinib over on the left. I've got 3 similar analogs that were predicted to be soluble, not only can I start to understand the rationale behind the predictions, but I can also get some ideas for how I can change this molecule to make it more soluble. And a lot of this is very logical. You can look over here, you added a hydroxyl group over here. Here you took this biaryl linkage and you made it into this pyrazolopyridine. In this particular case, you took this aniline nitrogen, substituted it for a methylene. So you can also imagine now taking this set of molecules, using these as an input to another technique like free energy perturbation. And you can look at this and figure out not only why the prediction was made, you can get some suggestions, and then you could predict whether, okay, is this still going to have activity against my target of interest? So this is a really cool technique. There are still a couple of gotchas, and the gotchas actually don't have to do with the work that Andrew White's group did, but they have to do with something that is not pointed out a lot about generative models. So generative models still, and this varies with the generative model, still have what I call the silly molecule problem. So generative models, people assess these typically based on, or they assess the validity of the molecules on 2 criteria. One is, can they be parsed? Can the SMILE strings be parsed? And that's typically, have I violated rules of valence? The other is, do they contain known reactive functionality? You can see here, you've got things that don't necessarily meet either of those criteria. These molecules don't violate rules of valence, but you're not going to get a triple bond in an aromatic ring. You know, this ring system does not exist in the universe in which I live. So, you know, there's some ways to get around this, but I think we still have this issue that we need to get around with generative models. All right, let's talk about another issue, and this is making effective use of 3D information. So if you take a look at the vast majority of what's being done in machine learning, it's being done with 1D and 2D representations. And this question comes up all the time when I give talks. So I did an online workshop for the Royal Society of Chemistry 2 weeks ago. And we were going through cheminformatics and building some basic machine learning models. And somebody asked the question, you know, why do you use 2D descriptors? Why don't you use 3D? Isn't 3D better? You know, 3D will capture the shape of the molecule. 3D can enable you to capture stereochemistry. 3D should be more transferable. And to that, I say maybe, and I'll get into that a little bit later. But, you know, why isn't 3D better? You know, I mean, you know, if you take a look at it, we've got 30 years of building pharmacophore models where we just define 2- and 3-point pharmacophores. We can encode that into a vector. That should be perfect for machine learning, right? Well, not really. And, you know, I think the reason for that, perhaps obvious, is that molecules have conformations. And these conformations typically don't contribute equally to your biological activity or to the property that you're trying to model. So we don't have a simple relationship between an object, a molecule, and a label, which is your activity or whatever you're trying to predict. Machine learning typically is set up to come up with relationships between a single object and a single label. That's not what we're dealing with here. What we're dealing with is multiple conformations. Each of these conformations has its own representation. So we've really got 3 different cases that we're dealing with. What we typically do is what we refer to as 2D single instance learning, where you have a molecule, you've come up with a set of molecular descriptors for that, and you're trying to associate that with some label. Then we've got 3D single instance learning, which I think the literature has shown, you know, unless you're doing some sort of alignment and you're being incredibly careful, just doesn't work. And then, you know, I'm really excited because there's been some interesting work published over the last 2 years on multiple instance learning. But I think multiple instance learning is still a field that's in its infancy. And when you look at most of the papers on multiple instance learning, the performance that they're getting is approaching the performance of 2D methods, but it's not better yet. So, my hope is that work will continue on this. Then I'd like to finish up by talking about uncertainty. Given a machine learning model that I've developed, and then I've got a new set of molecules, how confident can I be in the ability of the machine learning model to predict that property? So, one analogy I like to make is if I built a model to identify birds, and I trained this model on pictures of parrots, I think this model will probably do a pretty good job of identifying parrots, but I'm not convinced that it's going to do a great job of identifying penguins. So, I think we've got an analogy here with molecules, but it's not a clean analogy. So given a set of molecules on the left that I train my model on, and then if I have to make a prediction with the molecule on the right, how confident am I in the ability of the model to predict on that molecule? And the way that people typically do this is to calculate the similarity of the molecule on the left, or on the right rather, to all the molecules in the training set. And you can come up with this distribution of similarities, but it's very fuzzy and there's not clean ways to look at this yet. There's confidence that can come out of a variety of different methods. But again, I don't think we have the model applicability problem solved by any means. So, and then I want to kind of point out a hole in one technique that people tend to use to assess the generalizability of their models. So there's this technique called scaffold-based cross-validation. So in this, what you do is you train your model on a set of scaffolds. Then you look at the ability of the model to predict on a new scaffold that it hasn't seen. It seems like a logical idea, but let's think about what's going on here under the hood. You're training a machine learning model on this set of molecules, but what you're really doing is implicitly training the model on the set of interactions that those molecules are making. So in order for this scaffold splitting assumption to be valid, then we have to assume that scaffold A is making the same interactions that scaffold B makes. And I think that more often than not, that's not a valid assumption. So, one of the classic examples that I like to cite is Viagra and Cialis. Now, both of these molecules bind to PDE5. They're both potent inhibitors of PDE5. But if you look at the structure on the left, you can see that these two molecules bind in the site in an almost orthogonal fashion. So what I've listed in this table down here are the 10 residues in the binding site. And then a black box indicates that that molecule makes an interaction within 3.5 angstroms of that residue. So if we look here, there are 10 residues in this binding site. There are 5 interactions that are common to those two molecules, but there are another 5 that are not. So if I train a machine learning model on Viagra and analogs of Viagra, should I expect it to be able to predict on analogs of Cialis because they're making different interactions? And, as I said, this is not the I don't think this is the exception. So just here's another example. Kind of, this is like looking at my high school yearbook, but this is going back to inhibitors of p38. So what I did was I just pulled out a dozen diverse inhibitors of p38. And if we look at a similar map of how these molecules bind in the p38 binding site, again, a black square here indicates an interaction with the binding site. So we've got residues over here. We've got molecules along the y-axis. You can see that there are residues, methionine 109, that a lot of the molecules make an interaction with. But you can see also that there's a broad diversity of interactions here. So if we just take these interactions and we treat them as fingerprints and we just calculate the Tanimoto similarity between these, you end up with a median around 0.25. So in a lot of cases, and I'd argue, more often than not, when you've got two chemotypes, they're not doing the same thing in the same binding site. So, I kind of think of a scaffold split as perhaps a lower bound on what you can expect from your molecules, or from your model rather, but I don't know that it's the best way to do your cross-validation. So, in conclusion, machine learning is incredibly exciting. I am fired up because there's so much going on. There's so much incredible stuff going on right now where we're combining physics-based methods and machine learning. It's having an impact across the board, but I think there are still a lot of fundamental unsolved problems. We've got the issue of explaining our models. We still don't have a great way of representing molecules. I'm so jealous of people in bioinformatics, right? They've decided that sequence is the way to represent a protein. That's great. I wish we had that, but I still don't think we have the best ways of representing molecules. I don't think we have great ways yet of determining whether a model is going to be applicable. If you look at drug discovery, it's a multi-objective optimization problem. You're trying to simultaneously optimize potency, selectivity, off-target effects, pharmacokinetics. We need better approaches there. So I think we've got pieces of the puzzle here, but I don't think we've solved the puzzle yet. And I think really, in order for people to succeed in this, I think we need people who have the right combination. I love this post that Drew Conway put up, and it's more about data science, but I think it's really critical to machine learning and drug discovery. And we need to start training people so that they can program, so that they understand chemistry and biology, but also understand statistics so that they're not kidding themselves. Anyhow, I'll wrap up here. Really want to thank all my colleagues at Relay Therapeutics. This is actually a picture from a picnic that we had last week. It's the first time we've had everybody together in one place, I think, in a year and a half. I want to thank Andrew White for what I think is a really interesting approach to model applicability. And I think more than anything else, I feel like our field has benefited so much from the open source nature. I mean, people who know me know that I'm a zealot about this topic, but I want to thank everyone who releases their code with their papers. It's helped me. I think it's helped the field to progress. And, I want to thank all of you for your attention.
Thanks a lot, Pat. Thanks for a great talk. First question is from Apik. Do you want to take it yourself about how to compute affinity based on different interactions? Do you want to unmute yourself? Doesn't seem to be the case. I read it. How do you...
Hi, Pat. This is Abhik. I'm from AbbVie. So I just, curious to know that you were comparing Viagra with Cialis. Like this compounds actually interact with various interacting pockets, residues. And the thing is, often we actually, try to find the similarity of the interactions. But what if, like, you are interacting with different residue? different residues and interaction changes. So is there any way or technique to measure or predict potency or any kind of IC50 or those kind of values based on the different interactions or any kind of methods? I want a faster maybe technique, but people do like more of this molecular dynamics and things to measure those FEP. So just want your view.
I want a faster technique too. For me, it really comes back to physics-based methods, things like free energy perturbation. I think there have been methods published on using, machine learning-based scoring functions for predicting binding affinity. I think that a lot of the data sets that are used for those are inappropriate because a lot of those data sets will span a huge dynamic range. So you'll see people showing a good correlation, but they've got a data set that spans 10 logs, which is not reflective of what we're doing in drug discovery. I think we're doing some work on using molecular dynamics. That would be a talk for another day.
Thanks. Next question is from Andrew.
Thanks. Hi, Pat. Thanks for your talk. Really interesting. I want to ask a question regarding maybe interpreted potentially see between the first part of your talk when you talk about the model interpretability, and the last one is more about the applicability and confidence. So, for example, in the approach such as the counterfactuals, I guess each of the generated compounds may have a different confidence associated with prediction. So, I was wondering if this can be potentially an issue since you may have, let's say, some of these comparisons that are more or less relevant, or maybe you think because they share a comparable scaffold, should be generally fine.
Yeah, well, I think one of the things I like about the counterfactual approach is that you're typically generating molecules that are relatively similar to the input molecule that you're trying to understand the prediction on, and that's all tunable. So you can figure out exactly how far away from that molecule you want to go. I think there are a number of other approaches. Gaussian process regression has a nice way of providing confidence. There are other approaches. What I've found in practice, though, is those approaches will often give you very wide confidence bounds. And those confidence bounds are so wide that I'm not sure how to use them. The thing that I like about the counterfactuals, as I mentioned, is it helps me to start to tease out what's important in the model. And, as a bonus, it's giving me suggestions.
Yeah, thanks.
Thanks, Pat. Next question is from Christoph.
Okay, can you hear me?
Yes.
Okay, so my question is, what is your opinion on attention-based, transformer-based approaches, graph convolutional neural networks for small molecules? Have you worked with these, and what is your opinion on them?
Yeah, I have, not as deeply as I'd like to. It's something that we're experimenting with right now. I think one of the areas that I think is really interesting actually for attention, and there have been 1 or 2 papers on this now, is in this area of multiple instance learning. Because if you're doing multiple instance learning, what you're trying to do is take this large manifold of conformations that you have and collapse that down to the biologically relevant conformations. And I've seen some interesting preliminary work that people have done using attention there. So I think it's an interesting area. It's something that we're definitely looking into more.
Thanks. And next question from Jing.
Yes, great talk. I have a question about your predictive model. I'm wondering if you have used that model to predict a molecule's, it's a property called lysosomotropic property. I don't know if you're familiar with that.
I don't even know what that is.
So basically, so you use imatinib and nidatinib. I have published a paper with Sunny Shen that these two molecules have very different, they call it lysosomotropic, which means they differentiate their distribution inside the endosome and cytosol because of the different pKa properties. So, these molecules, once it enters the endosome, they actually, because of low pH, it protonates more, and then it's kind of trapped in the endosome because it gets more hydrophobic, so it cannot go through the membrane back to the cytosol. But the target of course of these kinases is in the cytosols. And I think this is a very important property of the molecules. You mentioned the imatinib, and but you have not used them to predict this differentiating. Yeah, I mean, you may not be familiar with this term, but
I get what you're talking about, and, yes. And I've worked on targets where I have similar issues. Yeah, yes. I think like any machine learning model, I think it's something that you could definitely apply machine learning to. It's just, do you have the relevant training data? Mm-hmm. Right? I guess when I think about building a machine learning model, there's always three aspects to this. There's the data, there's the representation, and there's the algorithm. And I think of them in order of importance that way. So to me, the data is always the most important thing. If you have a high quality data set that you can use and you've got data on relevant molecules, I think it definitely, you could do it.
Right, or you use a solubility example, but solubility is, to me, is most explainable, right? I mean, from the chemistry, physics point of view, is most explainable. And
well,
so
yes,
I'm just wondering,
no.
yeah. Yes. Okay.
I think actually, and I wrote a blog post on this, solubility is actually really complicated.
Okay, all right, thank you.
But that's okay. But yeah, I think it's worth a try.
Okay, thank you.
Thanks, Pat. Pat, you mentioned that you envy the bioinformaticians because they decided on which kind of representation they want to go for. Sort of like, if you look into the work that has been, is actively ongoing in developing new representations for small molecule, sort of like, what gives you hope, and what are the developments that you find most promising?
Yeah, I think there's a lot. So there's a whole area of work in developing learned representations. So using message passing neural networks, convolutional neural networks, and really using the set of molecules that you have to develop the representation and then use that to build your model. I think the really big open question there, and I could have spent another 20 minutes on that, is how big does your data set need to be in order to develop this representation? So, in the comparisons that we've done, learned representations don't start to be competitive with standard descriptors until you get into data sets that have, 3, 4, 5,000 molecules, which, if you're looking at a data set that you have within a drug discovery program, if you're at 5,000 molecules and you haven't gotten your clinical candidate, you have a problem. So I think, the big question there is, and it's, as far as I can tell, is still unanswered, is what's the relationship between data set size and the expressibility, I guess, or the expressiveness of your representation. But I think it's a really exciting field.
Yeah. Thanks. Okay, there's just another question I have to read. There was a question. I'm not sure I get the answer that why it is. Maybe you want to phrase it yourself? Let me take the last question.
Yeah, I mean, it looks. Oh, go ahead.
Yes, thank you very much. So at the very beginning, I seems to hear that it's not that desired for biologists to take the machine learning-based affinity predictions model because of certain reason. I didn't quite get it. So could you repeat it again to elaborate a little bit?
Yeah, sure. I think that black box models in drug discovery are useful, but there are a lot of things that they don't help you with. When I'm working in a drug discovery program, what I really want is a model that helps me to understand which molecule I should make next. And if my model is not interpretable, then what I have to do is I just have to give my model every molecule I can think of and get a prediction out. I would much prefer a model where I can understand why it made that prediction, help me to know what to do next, help me to be more confident in that prediction. And when the model doesn't work, I know how to fix it.
I see. Yeah, I think also there's some other works based on machine learning model. Their goals are aligned with what you have talked. They're also trying to insert some explanation or interpretability inside the model to get some understandable predictions based on the input. So I think what you say makes sense. Thank you.
Thanks. So I guess with that, we come to the social part of the meeting. I would like to thank Pat and Mohammed again very much for 2 great talks. And yeah, Andreas, I think you are the master. I hand over to Andreas for the intro on how we do this.
Yeah, absolutely. And first of all, thanks to both speakers as well, Pat and Mohammed, excellent talks. And a reminder that the next presentation or our next meeting will be on the 25th of November. If you would like to present, please just let Clara, Andrea, as well as myself know, please. And yeah, please stay on the line. So I will put people into breakout rooms, about 6 or 8 people per room. And in case someone sits in his own room, I will put that person together with someone else as well, of course. And basically just have a good chat, introduce yourself, and have a good and interesting chat. So thanks a lot, everyone, for the presenters in particular. Thanks a lot to everyone for attending, and see you on the 25th of November. And please stay on the line. Cheers.
Thank you.
See you soon.